Hello, friends, and welcome to another lecture on chemical engineering thermodynamics. This is Professor Arvind Prasad. Today, we will study how to do calculations to find the heat, work, internal energy, and enthalpy for an adiabatic process. What is an adiabatic process? An adiabatic process is a process where heat is not given to the fluid. The fluid here is an ideal gas. Now, let's have a look at the problem. 1 kilomole of an ideal gas occupies a volume of 4 meter cube at 600 kilopascals. It is compressed adiabatically to a pressure of 900 kilopascals. Well, to a pressure of 900 kilopascals. So I'll make that slight correction here that is not here, to a pressure 900 kilopascals. Calculate the heat supplied and the work done. Also find the change in internal energy and enthalpy. So let's get ahead with solving the problem. Now let's first visualize how does this process look like. So as usual, we go with our pressure and our volume axis. So the y-axis is the pressure, the x-axis is the volume, and to start with, the volume is 4 meter cube and 600 kilopascals. So we make this. So this is 4 meter cube and this is 600 kilopascals. Now it is compressed adiabatically to 900 kilopascals. So we draw this 900 kilopascals. Well, we really do not know what is the final temperature and the final pressure, but this is the final point. We draw it here, it's 2, and the initial state here is 1. And the process can be shown this way. It can be drawn like this. So let's draw it a bit neatly. So there we are. Yes, and it can be shown this way. Now remember, through 1 and through point 2, there's a unique isotherm passing. So there's an isotherm T2 passing through point 2, and there's an isotherm T1 passing through point 1. T1 is lesser than T2. Since we compress, the gas is going to get heated up. So to calculate internal energy and enthalpy, which are functions of temperature, it's imperative that we calculate the temperatures at 1 and temperatures at 2. That is T1 and T2. So let's go about doing that first. So what we have here now is we have a gas which is at pressure 600 kilopascals and its volume is 4 meter cube and its mass is 1 kilomole. 1 kilomole. Therefore, its temperature, applying the ideal gas law, is going to be PV by R. Yes, N into R. So that's going to be 600 kilopascals into 4 meter cube. R is 8.314 into N is 1. So let's do the calculation. So this is going to be 600 multiplied by 4 divided by 8.314, and that's T is equal to 288.669 Kelvin. So we have T1, which is nothing but 288.699 Kelvin. Now we need to find out T2. So we can Write the equation first for the adiabatic gas law, or the adiabatic process law, we should say. For the adiabatic process, PV raised to gamma is a constant, where gamma is nothing but Cp by Cv. Now, for an ideal gas, we can take Cp as 29.099 kilojoule per kmol Kelvin, and the value of Cv is 20.785 kilojoules per kmol Kelvin, and therefore we have gamma as 1.4. If these values are not given, that is the value of Cp, Cv, and gamma, for an ideal gas, we can take these values. So we have gamma. Also remember, for an ideal gas, over and above the adiabatic law, the law P1 V1 by T1 is equal to P2 V2 by T2 holds. Also, the ideal gas law PV is equal to nRT holds. So what can we do now? Well, let's take the first equation, the adiabatic law equation. It is P1 V1 raised to gamma is equal to P2 V2 the whole raised to gamma. Now, if we eliminate V in terms of pressure and temperature, then our problem is solved. Now, how do we go about doing that? We have P1 by P2 is equal to V2 by V1 the whole raised to gamma, which if we write, if we replace V2 and V1 with the ideal gas equation, we can write it down as R T2 by P2 into P1 R T1 the whole raised to gamma. And therefore we get from here P1 by P2, the R gets cancelled off, and we are left with P1 by P2 the whole raised to gamma and T2 by T1 the whole raised to gamma. Now, I do not wish to simplify this off. Without simplification also, it's possible that I could solve it out. So let's go ahead doing it. Sorry. You have 600 divided by 900 is equal to 600 divided by 900 the whole raised to 1.4 into T2 by T1, which is 288.699. A slight correction, it is 669 the whole raised to 1.4. Therefore, what do we get now? 600 by 900 makes it 1/3. 2/3 is equal to 2 by 3 the whole raised to 1.4 into T2 by 288.669 the whole raised to 1.4. And now that gives us 2 by 3 the whole raised to 1 minus 1.4. That's going to be equal to, let's do it, 2 divided by 3, the whole raised to 1 minus 1.4. That's 1.71. 1.76, which is equal to T2 by 288.699 raised to 1.4. So what we have now is we have to take the root 1.4 of this. So we go ahead and do it. So what we do is take 1.176, the whole raised to, start the bracket, 1 divided by 1.4, and that is what we have. We have 1.1227. Note here 1.176, the whole raised to 1 divided by 1.4 is 1.2277. 1.12277. This is equal to T2 by 288.699. Therefore, we have T2 as equal to 288.699 into 1.12277. So let's find out how much it is. 288.669 into 1.12277, and this is equal to T2 is equal to 324.108 kelvins. Now, getting this answer is the most crucial part of solving the problem, that is getting the final temperature. Now from here onwards, you'll see that the calculations become much simpler and we will end this problem very quickly. So the change in internal energy can be calculated by delta U is equal to N, which is 1 kilomole, into Cv, which is 20.785, into the final temperature, that is 324.108, minus the initial temperature, which is 288.669. So the value of delta U is equal to 1 into 20.785 into, start the bracket, 324.108 minus 288.699. That's 735.97 kilojoules. Well, delta H is N into Cp into T2 minus T1, where T2 minus T1 is 324 minus 288. That is the previous temperatures that we had taken here. So the calculation of delta H is straightforward. We can write delta H as equal to delta U over Cv into Cp. So we can take that, we already have the value of delta U here, we divide it with Cv, that is 20.785, and multiply it by 29.099. So that is 1030.366 kilojoules. So delta H is equal to 1030.366 kilojoules. So we have the value of delta H here. And how do we calculate the work? Never, in such problems, never commit to memory the formula for work. It's just not required. Apply the first law and you will get the answer. We all know that for an adiabatic process, Q is equal to 0. And by the first law, for closed systems, we have delta U is equal to Q plus W. This is equal to 0. Therefore, what is the work? It's fairly simple now. Delta U is equal to the work. How much is it? Delta U is going to be equal to 735.97. So your work now is nothing but 735.97 kilojoules. And why is this? This is because the heat given in the process is 0. So that was all about doing the calculations for change in enthalpy, the change in internal energy, and the work for an adiabatic process. I hope, guys, this was a very informative lecture for you as far as the calculation goes, and you found something very interesting here. Keep watching. Have a good time. Have a great day. Goodbye.